In this question, we are given a loop of radius A carrying a current I is placed in a uniform magnetic field. If the normal to the loop is denoted by the vector n cap, the force and torque on the loop are what? So this is our loop, right? So we have a loop like this, a circular loop. Current is flowing through it. So we will have a magnetic field coming. We'll have a magnetic field. And this is the radius of the loop. A is the radius of the loop. And let's take a segment ds which subtends an angle d theta at the center. Now the force on the loop, obviously we know the formula. Force on the loop is nothing but the integration of dl, which is nothing but the length of the loop. So here we'll take the small element ds, the length of the loop, cross product with the magnetic field and into the current. So this is the formula. So now ds I can of course write it as, so ds is nothing but we have ds, the small length, nothing but r the radius. I'll take r as the radius here, r multiplied by d theta, r multiplied by d theta. I'll take r here as the radius vector. Now the radius vector can be written out as, the radius vector is the, in parametrized form, can be written out as a, the magnitude of the radius, a sine theta plus cos. So we have a sine theta I and a cos theta j. So this is the parametric form of the radius vector. So now let's just have to substitute and do this integral. So I have I, and ds is nothing but a d theta and we have sin theta I plus cos theta j. So this is what I've written out here is nothing but ds cross product with pi. So this will give me, what this gives me is, so on evaluating the cross product, we get 0 to infinity, sorry, 0 to 2 pi. We have to so d theta is now going from 0 to 2 pi. Okay, so the integration is over d theta, so it's going from 0 to 2 pi I into a into b and cos theta d theta k vector, because I cross j is nothing but k. Okay, so I cross j is nothing but k. So we get k vector. Now this is a capital F. Okay. Now how do we calculate the torque? Torque is nothing but R into R cross F. So the small torque element d tau is nothing but R cross df. So df is nothing but the the term inside this integral. Okay, so ds is nothing but the term inside this integral. Without integrating, you get df. Integrated, you'll get f. So this is term inside the integral. So let me write it out. So r, the radius vector parameterized, has a form cos theta I plus sin theta j. Cross product and df is nothing but this quantity that we wrote inside this integral is nothing but iab iab theta cos theta. So this cross product, when evaluated, gives us a answer of minus I a square cos theta sin theta I. Now again, this is nothing but d tau. Now if you want to get tau, you have to integrate d tau within the limit 0 to infinity. So you just integrate this answer within the limit 0 to infinity. So when we integrate, what we get is, within the limits, we get pi a square I b j. So now this can be equivalently written as pi a square I. So this j vector can, now I can write it as cross product with the n cap vector. So n cap was defined as the normal to the loop. So I can define the j vector as the n cap cross b, because n is in the direction of the k vector, b is in the direction of the I vector. So k cross, so the cross product of these two vectors I and k will give the j vector. So I can write it like this. So therefore the right answer to this question is given by the option A.